Thank you very much. So let me start by thanking the organizers for putting this paper in this program as part of this really fantastic conference on heterogeneity. I am so happy to be here, if anything, because I'm really learning a lot. And I'm sure this will continue over the next 2 days. The other thing that I want to do is apologize with my discussant because he received the slides at 8 a.m. this morning as we've been working through the night to get some of the results that I'm going to show you. I did send the discussant a few months ago, weeks. A few weeks ago, a very earlier version of that paper that, an older paper that has a little overlap with what I'm going to present, but really not that much, as I will discuss in a minute. Okay, as you see from the long list of co-authors, it takes a village at the New York Fed to write a paper. Actually, many of these co-authors are former New York Fed RAs who, over the years, worked very hard to build a code base that made this project possible. And we thought it would be important to recognize their work and via the co-authorships. I should say that, as a matter of fact, the disclaimers that is at the bottom of these slides applies not only to the Federal Reserve Bank of New York or the Federal Reserve System, but also to most of those co-authors who have no idea on what I'm going to present because two people know very well. I mean, Donggyu, a new colleague, and then the two current RAs who really worked very much on this. Sikata Sengupta and Aidan Gleich, who is applied to graduate schools now. And, we were talking about greed. And he showed a lot of greed last night as he worked through the night to get the results. So I'm very grateful to him. Okay, I guess that concludes the introduction. Okay, so what I'm going to do here is two things. I mean, the main thing that I want to do is talk to you about a set of tools that, central banks, but arguably also, academics can use to estimate Hank on a routine basis, and in general, estimate models that are difficult and computationally expensive to estimate. And I'm going to use these tools as an application here in two things. One is a forecasting comparison applications, where obviously, by its very nature, you need to estimate this model over and over and over for many periods, which is, for quite costly, and we're going to make it, quote unquote, easy. And then I'll have, if time allows, a little bit on DSG VARs for Hanks. Although I don't have yet results in it, there will be in the final paper. And then, in terms of substantive contribution, I will use these tools, and for now, most of the forecasting comparison, to kick the tires of a frontier Hank model. And by the way, as Gianluca said earlier this morning, if you have any question, clarification, don't hesitate to interrupt me and ask them. No, the other way around. Okay, so in the paper that we sent Marcus, we've had a Hank model at the New York Fed for a couple of years now, but that model was a one-asset Hank model. And given what we wanted to do in this paper, it really made sense to take a frontier model. And so we took a two-asset model, that I will describe in a second, by Bayer, Born, and Lutlicke. Now, why did we take that model? Well, precisely because, if you read the paper, the title of Bayer, Born, and Lutlicke, from now on, I'll call them BBL, paper, is Shocks, Frictions, and Inequality in the U.S. Business Cycle, which is intended to be a riff of Smith and Wouters' Shocks and Friction in U.S. Business Cycle. And the whole point of the paper is to interpret the business cycle through the eyes of a Hank model and contrast it with the rank model, Smith and Wouters rank model interpretation. But of course, arguably, Smith and Wouters were able to write that paper because they had some validation suggesting that, their model was a model that could describe business cycle data decently. And one way that they provided that such validation is by showing that their model could forecast business cycle variables as well as if not better than reduced form models such as VARs. And arguably, this evidence was one key reasons why, after in the 2000s, a bunch of central banks, started using Smith and Wouters style DSG model. Because before, DSG models were viewed as just an academic divertisement. So, if BBL are going to tell us their model's interpretation of business cycle, I think it's important to ask, well, how well does their Hank model fare in terms of forecasting accuracy for business cycle variables compared to any benchmark, as Smith and Wouters seems like a natural one. Second, a related but important question is to whether incorporating distributional data / measures of inequality help or hinder the forecasting accuracy for business cycle variables. Okay, so that's what we're trying to do. Okay, a couple of caveats that are important. First of all, forecasting in itself is not an end-all for most people. And in fact, even from my perspective, it's not an objective per se. The whole point of forecasting, and this is why at the New York Fed, we publish actually every quarters our rank for so far, but soon maybe also a Hank, models forecast, is precisely to confront the model's prediction with the data. And that's one way of disciplining yourself and figure out where the model succeeds, rarely, and fails most of the time. And so that's, I think, one way, to really, one way to, force yourself. And second point, regardless of how well Hank forecasts business cycle variables, heterogeneity and inequality is important for policymakers, and for obviously rank models are silent about that. So there's a reason to study Hank models. Okay, let me spend really a couple of minutes, because this is not our model, so there's no point in me spending a lot of time on BBL's model. But maybe not all of you are exactly familiar on how the model works, so let me say 2 words. So this is an heterogeneous, in one sentence, BBL wants to be the heterogeneous agents version of Smith and Wouters. In BBL, heterogeneity arises from 2 sources. One is a persistently different productivity across workers, and actually there are, Gianluca mentioned earlier, income variability shocks that are countercyclical in BBL. That is one of the sources of the shocks in the model. The second reason for heterogeneity in their model is that there are both workers and entrepreneurs, and so randomly, a la Calvo, there is a switch from one to the other. So for instance, I'm Del Negro, a worker, I'm walking, and I may get tapped on the shoulder and become Sam Bankman-Fried and go make millions. And then, become rich, and then all of a sudden, I get tapped again and revert to being a Del Negro or worse. So that's, this example just shows that the model is realistic from that point of view. Okay, agents trade liquid bonds and illiquid capital differently from the Hank model of Gianluca and company. In liquidity here is modeled exogenously a la Calvo as opposed to transaction cost. And all of these features, as discussed at length, imply heterogeneity even PCs. So to this kind of heterogeneity structure, BBL add most of Metzenwater's bells and whistles, such as real rigidities, investment, adjustment cost, variable capital utilization, and nominal rigidities, such as price and wage stickiness. So that really the key difference between these models as Metzenwater's is in the representative, again, I'm just repeating something that's been repeated throughout the day, in the representative agents on their equation determining aggregate consumption. This implies that, when looking at the forecasting performance of this model, it would be particularly interesting to look at the forecasting performance for consumption, meaning we would really hope that at least in terms of predicted consumption, this model would do better than a rank model. Okay. Now, I wanted to talk about estimation in a broader sense, or like following up on Tom, talking about the challenges, and which are very interesting, in terms of estimating Hank model, or the econometric challenges of estimating Hank model. But since, and these are basically that, you want to fit, unlike in a rank that just fits a time series, mostly aggregate data, here you want to fit both time series and cross-sectional moments. And in the other paper, we talked about, trying to figure out whether there is a trade-off between fitting, again, aggregate data and fitting distribution. In BBL, really, we're going to, because in this two-asset model, computing the steady state is extremely costly. And so, we need to figure out how to computationally, we need something computationally very different from what I'm going to present today to really estimate the steady state parameter. That's not what we're going to do in this paper. So we're going to follow BBL, not estimate any of the parameters that determine the steady state. And so essentially then that implies that the method in terms of, econometrics is standard, Kalman filter for the various time series. And by the way, in terms of time series, they use the standard as Metzenwater observable, which you all know, plus a bunch of additional variables. Some are related to taxes because this model is non-Ricardian, so obviously having information about taxes is extremely important. And some, are of course related to inequality. So in particular, the wealth and income share of the top 10%. Okay, so as I said, let me skip this part, and I think get to the toolkit that I will try to promote. So we want to make repeated estimation for computationally difficult model feasible. Now the standard approach that, I don't know if you ever estimated a rank model is used, and that is currently used even for Hanks, as far as I know in the literature, is what's done in Diner, which is Markov chain Monte Carlo. In Markov chain Monte Carlo, the way that this works is that you start with one particle, so one particle, I mean one estimate, one draw for the vector of the parameters, and then you randomly visit the entire posterior distribution, and then you keep all these random draws, and you call it your distribution. There are a couple of problems with this approach for models that are difficult to, computationally challenging, both to solve and for which the likelihood is computationally challenging. I mean, one is a general problem is that this Markov chain model sometimes, they get stuck, and particularly multimodality is something that they don't explore very well. But for computationally challenging models, this is it's Markov, and being Markov, you cannot parameterize it, meaning that to get to draw J, 1001, you have to get to draw 1,000. So, you're kind of stuck. And this is not a great feature. So I'm going to propose a different approach. I'm going to briefly explain it to you and then argue that it can be more profitably used. So first I'm going to give you a somewhat superficial overview, which is like, as opposed to having one particle, you're having a swarm of particles, and then you let each of these particles travel. This may give you a vague idea of what the method does, but I want to give you a little more, I want to go a little more in detail so that, you can see that this method is actually readily applicable and potentially useful to you. So this method is called sequential Monte Carlo, and what it is incremental importance sampling. So importance sampling was one of the first approaches ever used to estimate any Bayesian model. What it amounts to is that if you have a posterior that you want to estimate, so the posterior is this last curve here. If you have a posterior that you want to estimate, but you don't know how, because it's not a standard distribution, what you can do instead is draw from a distribution that you know how to draw, let's say some Gaussian, and then use draws from that Gaussian as an approximation for the posterior that you're interested in. Well, how do you move one from the other? Using weights. And those weights are proportional to the ratio of the distribution that is your target and the proposal. Well, these importance samplings may work pretty well if you have a simple unidimensional system because, it's pretty easy to cover much of the real line. But if you have a many parameters, as this model have, you're dead in the water very soon because to the extent that your proposal isn't any good, 99% of the draws are going to go like in the middle of the ocean where the likelihood is 0, and only 2, will really get anywhere. So that means that if you draw even 1 million, you really have an effective sample size, which is that object over there, which depends on the weight, really, a handful. And as you can imagine, with a handful of draws, there is no robust inference can be conducted. Okay, so what's the idea of this sequential Monte Carlo? Well, let's start. Does this work? No. Okay, it works in the wrong way. Let's start by, multiplying the likelihood by an exponent phi n, and let's start with a phi n that is really close to 0. Then the target distribution is essentially the prior. Well, for that target distribution, the prior is a fantastic proposal, because if you want to fit the prior is great. So, you have a great set of particles with weights that are all uniform and everything is hunky-dory. But then the idea of this is that you can increase that phi n very slightly up, and the previous iteration is going to be a great proposal for the next iteration. Why is it going to be a great proposal? Because in between, you let the particles travel. If they didn't travel, you would be stuck with the original particles and you wouldn't have solved anything. But if you let the particles travel via, just like you do in Marco-Chain Monte Carlo, then they will move, right? They will move from here toward where the mass is higher in general, right? And basically that makes the distribution, better and better. Yes, please. Yeah, absolutely, right? I mean, you're familiar with Marco-Chain Monte Carlo. What do you do in that, right? You take you have a proposal centered at the old particle, you give it a random vector, and then basically you always accept if you go up, and sometimes reject, sometimes accept if you go down the posterior. That's exactly what I mean by make them travel. There might be more efficient way of that. Hamiltonian is another way that is better, but it doesn't matter. As long as these particles move in the right direction, then you got it. Okay? Yes? No, every time you go one step at a time. I mean, what's the problem here is the problem is that if the particles have zero weight, then you're kind of dead in the water, right? You don't want, right? And so as long as you let the particle move, okay. And if you do that gradually, then eventually, boom, right? You you make your problem harder and harder, but only incrementally. Then the end point is going to be a pretty good approximation of your final posterior, and you're home, okay? I mean, why am I just one more thing? What's going on? Okay. No, I'm going in the wrong direction. Yeah, one more thing. I mean, obviously, what schedule, or what rate should that phi n go to 1, right? That's, from a practical point of view, that's key. Well, Herb's have surefire for a rank model. They had a specific schedule, but that may not work for your model. And so we propose an adaptive system where basically you actually choose the step so that the effective sample size doesn't decrease that much. So at every step, the problem is made only gradually harder. Okay, so far, you may say, okay, the Negro, you just gave us another approach to random walk metropolis hasting. I mean, maybe we trust you that it's any better than metropolis hasting, but then what? So what? Why do I have to hear about it? Well, because it has some benefits. The benefit is that the particles, you don't throw them away. Every time, say you have a new data set, right? So you estimated the model up until last quarter, now you got a new quarter. You want to re-estimate the model. With metropolis hastings, you have to start from scratch. There's no other way. With this, you can use the previous quarter as a proposal for the new likelihood. Obviously, since the likelihood hasn't changed a lot because you just got a new quarter, then, what's the big deal, right? Boom, very quickly, you can, right, the particles will adapt, and you'll be done very soon. But I think that in general, this proposal, right, is for people who, again, want to estimate difficult model, is much more promising. Why? Because let's say that, as it often happens, you want to try robustness to a slightly different prior, change a slightly different things in the model, or use a coarser solution method. You want to start with a coarser grid and then, have a finer grid. Then, again, the same principle apply. The estimation that you just ran is arguably going to be a much better proposal than starting from scratch, starting from the prior. And so you can use that and do all the things that we do all the time when we write papers, pretty seamlessly in this approach. And so this is why it's important. But again, when it comes to estimating a model every quarter, because that's what you want to do for a forecasting comparison exercise, then this is really important. Okay, so I'm done with I'm done. And by the way, we already have a package that does some of that in Julia, and as a byproduct of this paper, we will build a new package that specifically does that for BBL Hanks model. Okay. Now, briefly, why estimation of the Hank parameters matters. This is actually using the one asset model, but I think we would find something very similar using also the two asset model. What I'm doing here is compare a forecast that I'm for, whatever, doesn't matter what variable, say GDP growth, obtained using an estimated Hank, where I estimate all the parameters, and one where I basically calibrate all the parameter except the shocks. And that's the thin line. As you see, you get pretty crazy forecasts if you don't estimate the parameters. So, there's a lot of value in just doing calibration, and we learn a lot from calibrated model, but if you want to use it in terms of projection, there is arguably the case that you may want to think about estimating these models. Okay, and now the stuff that we worked until 3 a.m. to deliver. These results, like all 3 a.m. obtained results, are very preliminary. So we'll see if they hold. But what we're going to do is basically take a sample period we use from 2000 to right before COVID. So we don't have any COVID data here in this comparison for obvious reasons. And we compare the RMSEs for various quarters ahead, 1 through 8, for 3 models. One is BBL with all the observables. The second is BBL using only the Smets and Wouters, so not using as observable at all the inequality and variables. And third, in green, the plain vanilla Smets and Wouters. I would not focus on period 1, because that's a nowcast. These models are not very good for nowcasting anyway. So, for instance, at the New York Fed, if anything, because the econometrician does not have the information and all the other people who nowcast, like a lot of high frequency data have. So when we run forecasts at the New York Fed, we always use somebody else's nowcast. So the fact that Smets and Wouters, does poorly for nowcast is not so important. But from 2 on, it's fair game to look at these RMSEs. And what we find is the following, that basically,
Are these quarters? What are they?
Yeah, so I'm forecasting quarters ahead.
Quarters.
Yeah, so 1 through 8 quarters ahead, 2 years, right? So basically, for GDP, from 2 on, there's not a heck of a lot of difference between Smets and Wouters and BBL. And actually, to some extent, BBL with just as Smets and Wouters does better than all of them in the short run. But really, from 4 quarters ahead, and to some extent, really, when you look at the DSG model forecast, it's 3 to 4 quarters ahead, the horizon that you're looking, not so much the near future. They're all the same. I think a very interesting result is that when it comes to consumption, this model seem to be doing a heck of a lot better than Smiths and Wouters. The results from inflation also they seem to be doing better here. To be honest, I'm a little suspicious of what's going on, partly to make the models comparable. We also estimated SW on the mean data just to follow BBL. Maybe that wasn't a great idea, but you'll see to what extent those results are robust. But I thought that the consumption result was kind of in line with what we would have hoped to find, and we're glad we did. Okay. The rest of the presentation is going to be something that we don't have results yet, but I'm just going to describe very quickly. It goes maybe in the direction of what Alistair was talking about earlier, which is trying to use a hybrid model to estimate the Hank models. And the idea goes back to an old methodology, which was called DSG VAR, which with Frank Scharfeide, we came up several years ago. And the idea is the following. A linear DSG model, including a Hank model, a linear Hank model, is nothing but a VAR on the observable with cross-equation restrictions. So if, here phi is the VAR parameters, and the black line is the likelihood, right, the describing the fit of the data, a Hank model just, puts a cross-equation restriction on this. So Hank model says that phi, the VAR parameters, are equal to phi star. Now, one way to judge how well your Hank model fits the data is to ask yourself, well, how much should I relax? So, I can view this cross-equation restriction as a prior for the VAR parameter. So if I believe in my Hank model, and I have to say, okay, how do the data, what's the VAR representation? How does the VAR look like? Well, my a priori belief is that the dynamics are those from the Hank model. And then I ask myself, how much do I have to relax my a priori belief in order to optimally fit the data? And so, the choices are as follows, right? If this line is very much in the tail of the distribution, so my Hank model is really bad, then the answer is that to fit the data, I really want to relax a lot the cross-equation restrictions. If, on the other hand, I'm close to the peak, I really don't want to relax them all that much. And so one way of judging the how good your model is by looking at something like this plot. So, for instance, the black line is for this Smiths and Wouters model. What the model tells you is, what I'm plotting is the marginal likelihood for this Smiths and Wouters model. What it says here is that, and lambda is the weight on the cross-equation restriction. What this plot says is that, this is the marginal likelihood of Smiths and Wouters, that if I relax the cross-equation restrictions, then I'm going to improve fit. So, this is clear evidence that the Smiths and Wouters model is misspecified. But at the same time, there is some value in this model, because if I relax it too much, the marginal likelihood goes down. And so I think it would be we haven't done it yet, but we will do it for this paper, to do the same thing for a BBL. And ask, and access that is the same thing. The other thing that I can do is, once I figured out how much I have to relax the cross-equation restriction, I can look how the dynamics in the VAR change from the dynamics in BBL. So I can decompose the VAR parameters into phi star, the BB, the cross-equation restrictions impose, the Hank model imposed dynamics, plus some deviation. And from learning about this deviation, I can learn something about where the model fails. Now, of course, just staring at VAR parameter is not particularly informative for anybody. So what you really want to do is to translate those deviations into impulse responses. So in this sense, and this goes back to the discussion that we had with, we were having with Tom and then Alice there, Alice's position is like we have, or which used to be Cristiano Ackermann's position, right? We know what the impulse responses look like from VAR. Let me write a model that is close to those impulse responses. The DSG VAR approach is a little different in that, since there is a lot of uncertainty quantitatively or how actually these impulse responses look like, let me use my DSG model as a prior and just figure out, how much relaxing the cross-equation restriction change the fit and the impulse responses. And we hope that this is going to be a useful approach to, again, kick the tires of Hank models. Okay, so let me conclude. We describe a set of tools that central bank can use both to estimate Hank on a routine basis and to assess their ability to fit and forecast object of interest. We use them for forecasting comparison, and we will use them in the paper, final version of the paper for DSG VARs. We kick the tires of a frontier Hank model such as BBL. Well, the results look so far pretty good.